Welcome to the course Machine Learning with Python. This is the second module. In this module, we'll explore the data scientist toolbox. Essentially, we'll look at the programming language Python. Let's have a look at the content for this module. We'll start with a quick recap, understanding what is Python and why do we use it. There are two versions of Python which are popular in today's industry. Python 2.7.x. Currently, we have Python 2.7.12, 1.2, or any version from Python 3.x. We need to understand which one to use and why are we using the one. Then we move quickly to understand the installation and setup process. We'll walk you through simple steps to understand how can we have Python on a Windows, Linux, or a Mac machine. Once we have the basics and the introduction set up, we'll quickly move on to understand the data types, functions, and important packages within Python. We'll then progress and look into data manipulation and data engineering, and finally add into data visualization. In this module, we'll spend a significant amount of time on data manipulation, data engineering, and data visualization. I presume you would be having some technical experience in any programming language. It would be, let's say, C, C++, probably Java or something else. So we won't focus on the core fundamentals of a programming language. We'll abstract a few things and we'll start Python at a relatively high level, which means that data types, functions, these are pretty much common to all programming languages you would have probably used in your professional career. So we'll abstract a few things and we'll focus on specific Python related things while we start this module. So let's get started. So let's start with a quick recap for Python. So we've already seen this slide in the previous module. We'll just take a minute over here to quickly go through the contents and get started with Python. So Python, like we previously discussed, is a highly popular, open source, and general purpose programming language. So when I say general purpose, it means that it is just not used for data analysis. It's probably used for a variety of different activities. Let's say something like web scraping, GUI development, game development, and probably many other activities. It's got extensive production support. So any application where it is launched into production, which means that finally it is deployed for real-time usage. It needs a variety of operational activities that needs to be monitored. So a separate team actually looks into deploying this into production so that it can scale to a different level. So Python in that environment has extensive support. It's the preferred choice for deep learning today. So today, if you look at the deep learning environment, we'll get into the details of deep learning in the later modules, but then as of now, you can understand it's a relatively new field within artificial intelligence. So for deep learning, we have a variety of frameworks or packages ready-made here and there. R is also having a fair amount of support for deep learning, but then in Python, we have a wide area of choices for one to get started with. Just a few examples: TensorFlow, Theano, Keras. These are just one of the few popular ones which are available on Python for deep learning. It's pretty much understood that very soon Python will overtake R as a preferred language for a data scientist. There are a couple of popular packages which actually made Python the preferred choice for machine learning in the early days. So Pandas and NumPy, these are packages where we have support for extensive data manipulation. Matplotlib, a library for extensive data visualization. SciPy, StatsModel, and Scikit-learn, these are the statistical modeling and machine learning packages for Python. Just a brief overview of the timeline. It started somewhere around 2009 when the rapid development or at the same time when Python was getting widely recognized for data analysis and data science. This is when Pandas came into picture. But then a couple of years before that, libraries like SciPy, which actually mimicked a couple of things from MATLAB, a couple of things from MATLAB's visualization library was actually converted to Matplotlib, and NumPy was actually reformatted version of numeric. This is where we have the most array level operations. And pandas is the data frame operation. Data frame is actually something which is analogous to a table from SQL, or let's say a sheet from Microsoft Excel. So the data frame level operations with pandas, array level operations with NumPy, data visualization with matplotlib, and a couple of statistical techniques in SciPy. And then somewhere around 2010-11, we had the package scikit-learn, which was launched, and that ushered a major role of machine learning with Python. So today we have a very structured, organized, and exhaustive list of machine learning techniques and frameworks available within Python. We'll explore a few things. We'll explore the couple of essentials which will help us get started. We'll first understand the basics of Python. We'll then understand the data types within Python. And then we'll explore NumPy and pandas. NumPy and pandas will help us get started with data manipulation, data engineering. And then finally, when we have data in the right format, we need to understand the data better by visualizing data. We'll explore matplotlib. Once we have finished with matplotlib, we'll have a command over the language where we'll be in a position to ingest, process, and explore data. So these 3 steps is what we would recommend for module 2. So another important topic to discuss before we get started is to understand which version of Python are we using. So are we using Python 2.7.x or Python 3.x, say Python 3.5 or Python 3.6. So in a nutshell, we can clearly say that Python 2.x is legacy and Python 3.x is the present and the future of the language. So it makes it very obvious. Why do we even consider Python 2.x? It's just obvious that we should consider 3.x for every practical thing that we do. There's a small trade-off over here. Before we look into the details and differences, some background. So while Python was getting very popular, there were a couple of trade-offs in the original language's compilers and the construction of the entire module. Now, the founders of this language actually thought before launching a huge version, that is Python 3.x, there are some core changes that they need to bring around in Python. Now, if they bring these core changes, it would have limited backward compatibility. It is important to do so because since the language is expanding and becoming popular at a different scale, it needed a couple of things fixed at the core and at the fundamental level before making a big leap forward. So that's why when Python 3.x was launched, there was no backward compatibility. It brought in few fundamental changes in the syntax, just a few. The most important change actually came in the print function and a few functions over here and there. Overall, I would say there is a huge overlap in the syntax and the format with minor changes between the two, but the problem becomes internally. So the packages or the third-party modules which supported Python 2.7 was actually supposed to be rewritten for Python 3.x because of the small syntactical and internal changes. So this support progress was actually limited for Python 3.x. So today probably every package you use will have support for Python 2.7, and they might not necessarily have support for Python 3.x. So that is a problem. But then coming to the differences, as we already mentioned, Python 2.7 has more number of libraries. It has extensive third-party support module, but then it has no major new releases. So the last version which we have seen in Python 2.7 was Python 2.7.12. Similarly, if you look for Python 3.x, so we have today the most popular one as 3.5. It's cutting edge. All new features have been added to Python 3 onwards. It's got limited third-party module support. So compared to Python 2.7, not all packages available over here have actually transitioned to 3.x, but then they are under transition. And it is under active development. So all new features, extensive rollouts are all happening under Python 3.x. So the question is, should we consider learning Python 2.7 or 3.x. Though there are only small differences from our level, I would recommend that we insist to learn Python 3.x. A few reasons. Most of the packages that we deal with in machine learning and data science have actually transitioned from Python 2.7 to 3.x. So we don't generally face a lot of issues while we work with Python 2.x, but then some teams might actually face. This actually comes into picture when, let's say, you're developing a large-scale application for a real-time company which needs to be deployed into a production support system. And in that production environment, there are a couple of packages which the team might be using, which might not be available for Python 3.x and are right now only available for Python 2.7. That might be a problem. But for most of them, for us at least for this entire module, we won't face any issues using Python 3.x. And anyways, since it is the present and the future of the language, I would highly recommend you to get started with Python 3.x. Let's get started with the installation and setup. The most recommended distribution is the Anaconda Python 3.5 version. So there are several ways to actually get started with Python. The most common and the easiest one would actually be to go to python.org and download the required version of Python and then additionally install required packages. So the packages which we discussed earlier, pandas, numpy, these are packages which you would probably need to install on a separate task. Or an easier alternative would be actually to leverage the Anaconda distribution. So Anaconda distribution is actually something from a company called Continuum, who have packaged together all the required modules and packages and the tools required for a data science project. So we can actually use the most popular one, which is 3.5. So right now in the market we have the 3.6 version also. But then for stability issues, let's stick around to Python 3.5. It's available for Windows, Linux, and Mac, and comes in 32-bit and 64-bit flavors. So while you're working for a data science project or a machine learning project, you'll actually need to use a couple of IDs and tools. The Spider, an ID which comes free of cost along with the Anaconda package. This is something which is analogous to Eclipse for Java developers or RStudio for R developers. Similarly, we also have Jupyter Notebooks. Jupyter Notebooks is the notebook kind of web browser interface to a programming language. So for Python, we can have the IPython kernel loaded with Jupyter Notebooks. We'll explore more of them in the next session. But all of this actually comes together with Anaconda's distribution. That is, after you install Anaconda's version of Python, you don't need to install separately Spider, Jupyter, or any other popular packages. Most of what we need actually comes along with Anaconda distribution. So how do we install that? So this is actually a Windows-based system. So I'm using the Windows version, but then the process is fairly the same for all of them. So for Windows, you can actually download the installer from Anaconda's website. You can choose the 32-bit or 64-bit flavor, and then just like you install any other software, you can double-click the exe file and install and follow the installation wizard. For Mac, you have two options. You have the graphical installation process as well as you have the command line process. The graphical process is just as similar to any other software which you install on a Mac, and the command line is actually something very similar to Linux. You can just invoke the shell script file which actually gets downloaded, and the remaining is automated. For Linux, again, like similar to the command line version of Mac, you have to download the installer and then invoke the shell script from the command prompt. I'll just take you to the website of Anaconda and just explore it, help you understand which version to download. So this is Python's official website. So in case if you're not interested in using Anaconda distribution, you can actually use Python's version and download the respective packages and install them separately. It's a very fair enough process. The only problem over here is, specifically for Windows, sometimes it's actually a pain to install all the packages. You might not find the most compatible version of the Python package on Windows easily. It sometimes becomes cumbersome. And then installing so many packages actually takes a while. So that's why I recommend Anaconda. But then this process is definitely a valid one. You can actually go towards download. You can find the recent version of Python 3.6.2. By the time you'll be watching this video, probably a newer version might have actually come into production. And we have now Python 2.7.14. Point 12 was a very popular one, and that was still released for a long time. If you go to Anaconda, so this is Anaconda's website, which is from Continuum. You actually have a graphical Windows, Mac, or Linux-based installer version. You can actually choose 2.7 or 3.6. I would actually recommend you to use 3.5 because that has compatible packages for most of the things we're using today. So you can actually use the respective version if you want a 64-bit version or a 32-bit version. But this will actually install 3.5, 3.6, and you would actually want to install 3.5. So for that, you can actually go to this website. It's the archive folder for the Continuum website. And over here, they have all the current and all the previous versions of Anaconda distributions. Now, this one, Python 3.6, is actually belonging to like Anaconda 4.4. So until 4.2, we had Python 3.5. So if you choose to download Anaconda 4.2, we would get the respective version for Python 3.5. That's an alternative way. Actually, the most recommended way would have been to install the Python 3.6 version, which is the latest one from Anaconda, and then create an environment within Windows or Linux or Mac environment for 3.5. That's a little long process. In fact, even though it's a recommended one, I'll go with an easy alternative. So if you go to this website, if you just hit search for 4.2, these sections get highlighted. So if you have a Windows-based system, you can actually take the 64-bit version for Python 4.2 and Anaconda 3. So this one, if you look over here, Anaconda 3, which represents Python 3, version 4.2 for Windows 64-bit. If you have a 32-bit system, you can actually go for the x86 architecture. And a similar version is available for Mac as well as Linux. So for Linux, you can actually just go ahead and choose Anaconda 3 86 if you have a 32-bit version, or Anaconda 3 4.2 86 64. This is the 64-bit equivalent for Linux. And similarly for Mac, you'll have two versions since you have the graphical version as well as the command line version. So if you have a 64-bit Mac machine, you can actually go ahead with Anaconda 3 Mac. Let me just check. Yeah. So this is the Anaconda Python 3 4.2 version for Mac OS 64-bit. This is the command line based installer, and you'll have a similar one for the graphical one, and that would be right here, Anaconda 3 4.2 Mac OS X 64-bit version. You can just play around. It's around 350 to 450 MB file, depending on the platform and the kind of flavor you choose for them. So since this is a 64-bit Windows system and I wanted to install Python version 3.5, I would choose this one, Anaconda 3 4.2 Windows 64. So I have it already installed. Once you download it, it's a very straightforward process. I've given you a basic set of instructions over here, but then this is a fairly straightforward task to get started with. Now that we have Python 3.5 set up, let's look at the data types offered by Python 3. So like any other modern programming language, Python offers a comprehensive set of basic data types and advanced data types. Let's huddle at them one by one. I'm sure you would have probably come across most of these names in any other programming language. So Boolean, integer, long, float, complex, string, dictionary, file, list, set, and a tuple. Most of these are pretty common ones which we have already in most other programming languages. So Boolean is a data type which actually stores values like true or false. Integer and long are data types which actually store numeric values with negative and positive signs. So something, let's say, like minus 10 plus 25 or 345 could be an integer value. The difference between integer and long initially was integer was limited with 32 bits of precision and long had unlimited precision. But with Python 3 and onwards, we don't have to know the differences between integer and long. So whenever there's a scenario where there's a scope for integer overflow, the data type is automatically converted to long. So we can ignore the differences between integer and long. Float would actually be the decimal value, 3.2, 6.3, or 1.456, and so on. Complex numbers are the numbers with a real and an imaginary part. Complex numbers do have a lot of use cases where they have to be used, but for this module, we'll temporarily ignore the usage of complex. String is another popular data type which can be an array of characters. So a character or a word or an array of words like a sentence or a paragraph could all be termed under the data type string. Dictionary is a special use case of key value pairs. You can store values with an appropriate index that you would like to recall it later on. File is a special case which we will explore in much detail in the coming sessions. But for now, I'll abstract file as, let's say you have a CSV or a JSON file on your local hard drive and you want to import that to your Python memory. You'll actually use a file data type. It's not a data type, it's just a means to import files or data from outside the Python environment. List is one of the most popular and commonly used data type. It's actually a collection of homogeneous and heterogeneous objects under one roof. Set is a modified version of a list where all the values in a set are unique. So you won't find duplicate values inside a set. A tuple is another modified version of a list where once the values of a tuple are set, you can't change them. That is, you can't change the values once a tuple has been defined. So in this basic set of data types, it's fairly straightforward to understand the differences between Boolean, integer, long, float, and probably even string. But then let's take a little better shot at understanding dictionary, list, set, and tuple. So when do we use a list or a tuple or a set or a dictionary? List can be used when you need an ordered sequence of homogeneous or heterogeneous collections whose values can be later changed in the program. If you do not want the values to be changed later in the program, it would be recommended that you use a tuple. A tuple is used as an ordered sequence of heterogeneous collections whose values need not be changed later in the program. Set is ideal when we don't have to store the duplicates and you're not concerned about the order of the items. And lastly, a dictionary is an ideal data type whenever we need to reference values with keys. So you have custom indexes or you have custom way of referencing a value which can be attributed as a key value pair. Dictionary would be a more appropriate one. Now to take a better understanding of all these data types, let's have a bit of hands-on exercises. We'll now move to a demonstration in an IDE called Spyder. Spyder is an IDE provided by Anaconda. It comes along with the distribution. You don't need to separately install it if you have installed Anaconda's distribution of Python. It can be used as an integrated development environment, and it's in fact analogous to most of your IDEs like Eclipse for Java developers, IntelliJS for Python and Java developers, RStudio for R, and so on. Let's have a hands-on exercise to understand these data types in depth. This is the Spyder IDE. Spyder IDE comes along with the Anaconda distribution for Python. So in case if you have installed Python 3.5 from Anaconda's distribution, Spyder would already be installed in your system. But in case if you have used Python 3.5 from python.org and you have installed all the separate modules using the pip command, you would need to use the same command to install Spyder separately onto your system. So this is Python 3.5. Let's have a quick visual tour of the entire IDE. It's very similar to probably any of the popular IDEs we have used for any other programming language. So towards the left, we have the Project Explorer. Project Explorer comes in handy when you have several Python files hierarchically organized under a folder structure. So navigation between the files, organizing files into different directories, packages becomes very easy with the visual tool for Project Explorer. In the center, we have the code editor. So a majority of the coding you do actually comes into this window. You can create several new tabs over here, and you can switch between tabs. I can write most of the codes into these commands, into this space. You can also write the codes and commands into the Python console. So towards the right bottom, we have the console. Now Python being an interpreted language, it gives you the freedom of directly firing in the codes or commands into the console. So let's write a simple program. I'll say hello world, probably the first command you'll fire in any language using a print command. You can see the output comes in directly into the console. Now we could actually write most of the codes in the code editor rather than using the console, so that you can actually have a visual inspection of the codes while we are executing them. On the top right, we have three tabs. We have the Variable Explorer, we have the File Explorer, and then we have the Help tab. Variable Explorer comes in as a handy visual tool to examine what values do we have in different variables. So in cases of debugging, in cases of scenarios where we want to see what values are stored inside a variable, rather than using the console in a dirty way, you can actually use this intuitive variable exposure visual tool to examine the values in different variables. The File Explorer comes in handy when you export or import files from the project directory into Python, in scenarios where you're reading data from a CSV file and then doing some analysis and exporting some plots as images or intermediate outputs as CSVs. All those files can actually be explored visually using the File Explorer. And finally, the Help tab. You can find a couple of handy help commands as and when required. We'll explore the Help tab as and when required. Let's get started with the data types. We'll now practically see what different data types has Python to offer. We'll look into basic ones and then little advanced ones with a couple of examples. Let's start with integers. We'll create a simple variable. Let's say we create variable a and we'll assign any numeric value to this. It could be, let's say, 101. Now, an integer value in Python can take a number of any size. Now, since we already discussed, whenever there is scope for an integer overflow, Python automatically typecasts an integer to long and increases the precision. So we don't really need to bother about int and long. We can just go on typing a large number into any variable, and the entire process of typecasting it and allocating more memory happens internally. Now, the way I would execute this command, this being a Windows system, would be I would select or highlight the command and I would press Control and Enter. This would be different in the Mac or Linux system. In Mac, it would be Command Enter, and in Linux, probably it might be Control Enter, similar to Windows. I will leave this to you, just the reader, to figure it out. For Windows users, you can choose Control Enter to highlight and execute the command, or you can also type in the command into the console and execute it. Now, to check the type of the data or the data type, Python actually provides a command called type. So if I say type of A, and if I execute this command with Control Enter, you can see that data type is int. This would have already been visible with the variable explorer also. So there's a variable name called A, the type is integer, the size is 1, and the value is 101. What we need to bother is probably the value, the name, and in some cases, the type. You can also do a lot of mathematical operations on the data. So let's say, like any other language, you would want to execute some mathematical operations like addition, subtraction. It's very straightforward and similar to what you have learned in the past. So I would say, let's say a is equal to a plus 6. And if I want to execute this, I can see the new value is now updated, 107. I can verify that with a print command. So let's type a print command as a print of A, and you can check the value here. So the value is 107. If you want to check the type of A, again, that would be int. Similarly, you'll have additional mathematical operations. Let's say something like A is equal to A minus 8, or let's say take a larger number, A minus 89. That gives a negative number. Oh, sorry, since this is a large number, let's say 890. Now we should definitely have a negative number. I can do a print of A, the value is minus 872. Type of A, it's still an integer number. Now, there are scenarios where a number is typecasted to another data type to avoid precision loss. So, for example, we would go ahead with a division operation. So, A is equal to 87 divided by 12. Now, the resultant number will actually be a decimal number. So to avoid, so had this been just an integer number and it was supposed to remain an integer number after the execution also, there would have been some sort of loss in the precision. So to avoid that, to avoid information loss and precision loss, Python would typecast it automatically to float. So if I execute this number, you can see that the data type changes, the value is 7.25 and the type is float. This would be the same if we had something like let's see, we again have A is equal to 101. Now A is integer, and I will say A is equal to A divided by 12. Now the assumption would be A is integer, like we see over here, and the resultant A after the execution also should be integer. But that won't be the case. So since we divide 101 by 12, we would actually typecast that to a float number. There you go. You can see the type has changed, float, and we have the new value stored over here. Now we've covered integers, we've kind of covered float, and the kind of arithmetic operations that's possible with integers are also possible with the same data type float. Probably all of them, which falls under the Bodmer's rule. Let's look into a very simple data type called Boolean. A Boolean is a data type which actually stores value of true and false. Now in Python, instead of using the values 1 and 0 for flag, you can actually use the value true or the value false inside a variable. Now, if you create a Boolean variable with a Boolean value, let's say flag is equal to bool, and you execute this command, by default, we'll have the value false stored in it. In some cases, when you override the value, you can actually say flag is equal to true, and we'll have the new value coming up over here. And this data type remains bool. Boolean is actually a very handy data type in cases of conditional statement execution. So when an if clause or a while clause, you have to check a condition. Boolean variables, since they have the values only as true or false, becomes extremely handy to check and proceed. Next is another popular data type called strings. So character arrays or strings are the most popular way to store text variables. So I'll say A is equal to my name is XYZ. And if I store this and execute this, you can now see that the data type is str, which stands for string, and we have a string value over here. You can do some string related operations over here. Now, Python provides a rich set of functions associated with the string variable. So for example, let's say you wanted to reverse a string, you want to capitalize a string, you want to slice a string, or you would like to, let's say, check for some substring positions. All of those functions are already made in string. We can actually, we'll look into this later. I'll just show you an example. Now, since this is Spider, you'll actually get autocomplete and function lookup also. So since A is a string, let's say I execute this and A is a string, and I would say A dot, the kind of functions associated with the string comes up. So we have an exhaustive list of handy functions for string operations over here. So probably anything you would have already used with strings in something like Excel or R or something like Java or C++, all of them have been neatly added into this exhaustive library. So let's say had this value been my name is XYZ with a small m, and we need to capitalize this letter, so we can use something like a dot and say capitalize. We call this function. We can see the value will have been updated. Oh, my apologies. We would say a dot is title, or let's say if we create title. Yes, title. So this would actually capitalize the first letter of a sentence. As we see over here, my name is Khan. Sorry, my name is XYZ. My bad. Alright. And then we have a list of other commands like a dot strip, split lines, start split. So all of these functions we'll be using in a while we do data engineering and data manipulation. So all of these functions actually come in handy. So is alphanumeric, is alpha, is decimal, is digit. These are functions which are used very frequently, and then we do slicing and dicing across strings. All these functions are very handy while we do string data operations and data manipulation in the upcoming sessions. Another way to concatenate a string would be, I would say, let's say you have a new string called B and you want to concatenate A with the new variable or the new value. I would say just a random sentence, please ignore the grammatical syntaxes. Yes, so you can see that the new value is now, my name is XYZ, without a space, and I am cool. This is how you can concatenate two different strings. If you want to make it more neater, I'll just say concatenate a space and then this one and then go on as long as you want, and this gets a little neater. So that's strings. We've just seen a sneak peek into the data type. There are several other possibilities and functions that we can play around with the string data type. So we've covered four important and basic data types. We've covered integers. Sorry, let's start again. We've covered integers. We've covered float. We've covered string, and we've covered boolean. Let's look into a couple of more advanced data types offered by Python. We now need to look into something called list, tuple, set, and dictionary. Now, out of all these four, we'll be very frequently using the data type list. So like we already learned, list is a collection of homogeneous or heterogeneous objects with Python in any order. So let's say we have four different values, let's say numeric values 1, 2, 3, 4, and then we want to sort them into a list. So I'll say list 1 is equal to, now this is a syntax to create a list. We'll actually put the values inside a square bracket. I'll say add a few numeric values like 1, 2, 3, 4, and 5. These are homogeneous values. If I check the list, I can see that the name list1 comes with the type list. It has a size of 5 elements, and these are the values. I can access each individual element with the appropriate index. So as a list of 1, and I'll take the 0th element. So indexing in Python starts with 0. So let's say if I say list 1 0 index, I'll actually get the value 1. As you see over here, we have the value 1. I can actually make something like something more random. I'll say list of 4. I'll get the 5th value in the index, that is 5. I can actually take a start point and an end point. I'll say everything from 2 to 4. And I'll say that whatever starts at 2, which is 0, 1, 2, the third one, up to the fourth one. And this goes on. We have additional handy ways to navigate through the list. So let's say everything from the second one onwards, from the second index onwards. So I'll get 3, 4, 5. And we have a couple of additional ways to handle them. Now, lists can also be added with new elements. So let's say I have list 2 is equal to 3, 4, 5, 6, 80, and I execute that. So I have list 2. And if I want to create a new list, list 3, which is a combination of list 1 and list 2, that is possible by just this concatenation statement. I'll say list 1 plus list 2. And if I execute this command, I can see the list 3 is a combination of list 1 and list 2 with the size 10. List also provides you additional handy commands. So let's say if I want to check something whether it exists inside a list, or I want to check the length of a list, you can just say list 3 and just say dot. Spider provides you the list of commands that are already available. So let's say I'll say list append, and I'll say append a new value called 98, and I'll check the value over here. So the value is now updated. So I can just say a list print list 3. You can see that the value has now been appended. I can see the length of a list. Length is a universal command. Length of the list, it's 11. Let's look at a couple of more inbuilt functions available over here. I can say list count, extend, index, pop, reverse, sort, several of them. We look into a couple of more as and when we require a list. But for now, I think this would suffice. Now, this was a homogeneous list where all the elements inside a list were of the same data type. But that's not necessary. You can actually have something like a list of an integer number, a decimal number, a string, and another list probably, let's say 1, 2, 3, 4. And if I execute this, I have a new list, which is a data type list, and has 4 elements. The first element is an integer, the second element is a float, third element is a string, and the fourth element is the list itself. Now I can create a list of nested lists in itself. We'll get at the complexities and what all other formats exist, and probably what other operations we can do as and when required. Let's move on to the next data type, which is tuple. Now, the difference between list and tuple is very straightforward. The primary difference is tuples will actually be loaded into the memory once and can never change it. So with list, in this scenario, let's say we want to access list new and the third index, which is the fourth element. So I'll get the value, which is again a list 1, 2, 3, 4, 5. Now what if I wanted to update it? I could say the access that appropriate number, and I'll say I'll update it the new value, which is a string value. Now it gets updated, and if I check or print the list, I can see that the list is now updated with the new value. You see this? We have the new updated value over here. But there are scenarios where, let's say, if you assign a value to a list, you would probably want that to remain same throughout the program's execution. Or probably you would have strict rules that these values should not change or they should be immutable. That's when we have a tuple. So let's say we have this list new, which is the new list which is created after modifying this value. These values should be the final ones, and no one should be given the permission to alter these values. That's when we can use the data type tuple. Once a value is stored inside a tuple, we cannot change it. So for example, we create a new tuple, let's say tuple 1 is equal to tuple of an existing list. Let's say we create it out of list new. So now this would be a tuple. Now if you come over here, tuple 1, the type would be tuple, size would be 4. And the good part of this would be it's immutable. Now we can access the elements of a tuple similar to what we have done for a list. So I'm saying tuple of 1, 1 would be the second element of the list. We can actually access that value. But then if I want to change it, let's say I want to change it to a new value, I would say update it to 100. Now if I try executing this command, you can see that we get an error message saying that tuple object does not support item assignment, which means we cannot change the value during the course of the program execution. So that's the difference between list and a tuple. We have one more data type which is almost similar to a list, and we call it a set. Now, this is similar to the set theory which we have learned during our college days in mathematics. We create a set of objects where duplicacy is an issue. So you cannot have duplicate elements inside a set. So let's say we create a set from a new list. I'll say set1 is equal to set of list underscore new. It's the same process, and you can see that we have a new data type over here. Then we execute this. Let's say we print this. We have the values over here. String 1 and new value. You can definitely change the values of the set elements. The only difference is you cannot add duplicate values. But in case if you add duplicate values, it won't throw you an error, but it will just remove duplicate values. So for example, let's say we have a set called set new, and we're creating a set of a list of 4 elements. Let's say 1, 2, 3, and 4. Now this would be a perfectly valid set. We'll have the values over here. My apologies. We made a small syntax error over here. Yeah. This will be a perfectly valid set. If I execute this set new, we can see that there are 4 values over here. But let's say if we add duplicates over here, we add 4, 4, 4, and 4. So we have 5 instances of the value 4. But if I execute this command or code, it won't actually throw an error. It's just that it will remove the duplicates, and if you check the values in set new, there'll still be just 4 elements. If we add a couple of more, let's say we add something new, 5, 5, 5, that new values will be incorporated over here, and you can see that the values are non-duplicated ones. So we use a set when we are least bothered about having duplicate values. It's just that we just don't care about duplicate. We just need unique values, and you don't want to actually take care of ensuring that every time an element is added into a list, there are no duplicate values. So in that scenario, set would be an idle thing. Now, like indexing in list and tuples, indexing is not supported in the set data type. The last part, or the last data type which we would like to cover in this section, would be a dictionary. So dictionary is a scenario where we want to access values with a key value combination. So let's say we have something called dict1, and we're creating a new dictionary with, for dictionaries, we create dictionary1 is equal to curly braces, and then we put in an index a with some value. It could be, let's say, 1 to 3. Then we'll have another value separated by a comma, let's say b, and we have the value some string, let's say the. This is a dictionary of 2 elements. Now, if you look over here, we have the dictionary 1 created with type dict, and it has size 2, and it has 2 elements, 123 and the. But the way you access the dictionary would be with the index you have created for that particular value. So if you want to access 123, the index corresponding to 123 is A. That is, it's a key and a value pair combination. So if you have it A as the index, we can actually access the value. We've not A. Oh, sorry. There you go. You can see the value 123 being accessed. You can then access the remaining values. Let's see, access with B. You can access the. So you can actually have homogeneous as well as heterogeneous values inside a dictionary, and you can append the values to a dictionary, you can add more values to a dictionary. It's just like the same stuff. So let's say I will say dict1, and I'll say a new value t is equal to 100. And if I execute this, I'll have the values updated with the third key value pair. But whenever you want to access any data type or any data values with a key value pair combination, dictionaries are the ideal ones. This comes in handy specifically when you're handling JSON files. You have specific use cases where dictionaries are extremely useful. We'll have all of this in practice in the upcoming sessions when we get hands-on with data engineering. That's the time when we'll have majority of the codes and majority of the functionalities of these four different data types exploited to a different level. But for now, just for the basics, I just wanted to showcase the four important data types, basic ones like Boolean, integer, float, and string, and the more advanced ones like list, tuple, set, and dictionary. Next, we'll actually look into something more advanced within Python. That would be NumPy and Pandas. NumPy and Pandas provide us an easy way to handle array operations and data frame operations. We'll get into the details, but let's get back to the slide. So let's explore NumPy. NumPy is a Python-based package who provides main object, which is the homogeneous multidimensional array. It also provides us with a vast collection of functions that help us with linear algebra, fast Fourier transform, and trigonometry. It also has a very sophisticated random number generation module. In the bottom section over here, we see a sample code to use NumPy. We first import the package NumPy as NP and create the object NP. Now, Python being an object-oriented language, you'll see a lot of similarity with Java or C++. Now over here, we say a is equal to np.arrange and a parameter 15. For the moment, ignore the second half. Just concentrate on the first half. A is equal to np.arrange 15. So you're invoking the function arrange from NumPy and we're passing a parameter 15. So what will happen over here is it will create a NumPy array with 15 elements. It will start from 0, end at 14, and it will be one dimensional. That is, it will have just one row. Now the resultant object is again a NumPy object. So this function, reshape function, acts on the output of this function and will augment the dimensionality of the resultant NumPy array into a different one. So the output over here would be 15 elements in one row, and that is augmented into 3 rows with 5 elements each. This is very similar to what you would have already seen in Java in case if you have exposure to it. Now when you print the output, this would be the output in the terminal. Towards the right, you'll see a sample visual example of a NumPy based array. Now this is a 2-dimensional array where I have highlighted the indexes in gray. So you can see the column based indexes range from 0 to 2 and the row based indexes start from 0 to 10. It always starts with 0 and ends with the length of the respective column or row. Let's have a quick overview of NumPy with a couple of practical codes. We'll explore a couple of them using Spyder. We'll quickly create a couple of dummy NumPy-based arrays and augment them with a couple of functionalities that are already provided. Towards the end, we'll have a basic overview of what kind of functionalities are available within NumPy and how can we leverage them in the further sections. So let's get started. We'll first import the NumPy module. Now once we have imported, let's create a dummy array. So I'll create a NumPy array as a1 is equal to np.array. And then let's pass a random list, a list of, let's say, 5 elements. Now over here, we can see that the name a1 has an array of 5 elements. You can just do a print to verify the same. There you go. You can see the elements over here. Let's do a type of a1. And you can see this will be a multi-dimensional NumPy array. Even though this has just one row, it is considered an ND array because the other dimension will have a value of 1. We can also create a multi-dimensional array using the basic functionality over here. Let's create a2 as numpy.array and we'll create a multi-dimensional array. So what we do is we nest 2 lists within each other. So we have 1, 2, 3, 4 and 5 and another list 1, 2, 3, 6. Some random numbers. Now this would be a NumPy array of this dimension where we have 2 rows with 5 columns. We can actually check the shape of a NumPy array using the shape property. Now A2 being a NumPy object, you can invoke the shape using the dot operator. I would say a2 dot shape, and you can see the shape is 2 rows and 5 columns. We can also augment this. Let's say you'll say reshape them as 5 into 2. Now I've reshaped that. This is similar to transform. You can also transpose, and then you'll see the resultant vector here. You also have a lot of mathematical operations available with NumPy. So let's create another dummy array over here with some different values. So let's say we have a couple of values different over here and a couple of values different over here. All good? So we have A2 and we have A3. Both of them are a two-dimensional NumPy array with the dimension 5 into 2. Just to confirm, let's print the shape of A3 also. You can see over here, it's a 2 by 5 array. Now we can do arithmetic operations in this. Let's create a new NumPy array A4, which is a resultant of addition between A2 and A3. So A2 plus A3. I'll have a resultant matrix or array with the values added element-wise from both the NumPy arrays. You can also do a dot operation or the matrix multiplication. So for that you'll say A2 dot A3. But the basic rule of matrix multiplication or array multiplication is the number of rows over here should be equal to the number of columns in this one. So let's just reshape this for the matrix multiplication to be possible. So A2 has 2 rows and 5 columns, and A3 also has 2 rows and 5 columns. We'll augment that into 5 into 2. So this resultant matrix will have 5 rows and 2 columns. And when we do a dot multiplication between the two, we'll have an end output with 2 rows and 2 columns. Let's see. Now if we have A4 printed, we can see this is the matrix multiplication of two matrices with the dimension 2:5 and 5:2. So the end output is an array with 2 into 2 dimensions. We can also do a lot of trigonometric functions. So we invoke the trigonometric functions directly from NumPy. So let's say A5 is equal to np.sin of A4. And we get the resultant value in A5. We can also do A6 as the cos trigonometric function. So we say np.cos and we get the respective values in A6. So as you see over here, we have the resultant values stored in this value in this matrix A6. Now we can also do square operations. So if you remember the old trigonometry rule, sin square theta plus cos square theta is equal to 1. So let's say we create A7 as A5 square. Square is leveraged over here with the double asterisk operator. And then we say A6 square. This is analogous to saying sin square theta plus cos square theta, which is 1, which means that the resultant matrix A7 will have values all 1s. That's it. So NumPy also provides you additional functionalities to create arrays with a single value. Let's say we have something like we want to create an array of 10 elements with all zeros in it. So we'll say np1 is equal to np dot zeros, and we provide the number. Let's say we provide 10. So we have an array of 10 elements with all values as zeros. We can also reshape this to our convenience. And if you want to cast it to a different format, we'll just say deep type is equal to int. If you see over here, the values over here have a data type of float. If you want an integer based array, you can actually create them too. So I can see this np1 will have all zeros. Similarly, we can also create an arrays of all ones. The only change being instead of np.zeros, we call np.ones. And that's it. We can see np1 will have all ones. Similarly, if you want to create an array with a different shape rather than just having the values 10, you can just create with the respective shape. So let's say we have a need for an array of 4 rows and 5 columns with all zeros. So that becomes our NP1 array with the respective shape. So in a nutshell, we've explored a couple of basic functionalities offered by the NumPy object and the NumPy package. So if you want to explore further, you can just see what all functionalities are actually provided by the NumPy package. One thing which we missed out was you can actually do a sum of the entire array. So let's say we have the array A1. These are the values. You can say A1 dot sum and we'll give a sum for the entire array. Similarly, we have min and the max operation too. There are a couple of others. I would recommend all of you to explore the NumPy package and see what all different functionalities are offered over here. There are a couple of other elements which we would require, and we would explore them as and when required during the data engineering and data feature engineering process. For now, this would be a comprehensive and basic overview to the NumPy package. Let's explore one of the most important packages in Python, Pandas. Pandas is where Python started getting traction from the data science community. It provided one of the most intuitive interfaces to handle and manipulate data. Pandas is essentially built up from two parts, series and data frame. Series is a one-dimensional labeled array capable of holding any data type. You can see a sample Pandas series over here with 8 rows and an associated index. The data frame is a two-dimensional labeled data structure with columns of potentially different types. But this is analogous to the Excel spreadsheets or SQL table. Over here, we can see that the rows have an index as well as the columns have a column index. But we can access one of these elements with the row index and the column index. Now this, unlike other data types, can have numeric values or even string values. We can alter the index values as per our convenience. Now to note, the series is the data structure for a single column. So essentially, the data in a data frame is actually stored in memory as a collection of series. So technically, data frame is built on the foundation of series. Let's look at Pandas from a deeper perspective. This being one of the most important packages for our data engineering and feature engineering activities, we'll spend a little extra time on this, figuring out what all does the package offer. So to get started, let's have a sample dataset from the internet. I would request you to download this dataset, which is an HR Analytics dataset from Kaggle. It's freely available and it's around 500 KB in size. If you go to this link, it will take you to the Kaggle website. Please create an account over here and download this dataset. I have already downloaded this dataset and kept it ready for the analysis. So I'll just copy the path and come back to Spyder. To load data into the memory, we'll first need to import the package pandas as pd. Once we load the package into the memory, we need an interface to load the CSV file from the hard drive into the memory. Now, Pandas offers a variety of interfaces to load different types of files. It could be a CSV file, it could be a JSON file, it could be an HTML file, and probably anything else. Since this is a very simple exercise and I've kept the external dataset a simple CSV file, our task right now will be very straightforward. We'll create a variable called df, which can be called as data frame, and we invoke the pandas function to load the data. So we say pd dot read, and you can see a variety of options have actually opened up. So let's take the simple one, pd dot read csv, and then we pass the path for the file. Now, since this is a Windows system, I would like to point out one additional thing. The forward slashes over here will not actually work with Python. You would actually need to use a Linux compatible version of slashes. So if in case you're planning to use the forward slashes, you need to use an escape character. So essentially, had you been using the forward slashes, you would have need to use an escape character, and then you could have leveraged that. Or you can use a Linux-based convention to load the data into memory. So I'm accustomed to the Linux-based type. Now let's just copy the file name and load this into memory over here. Now, there are a couple of extra parameters over here, which I'm ignoring for the time being. Now, since this is a very clean and neat data set, We don't need to pass in additional parameters to get the data in the right format. Let's load the data. And as you can see, the data has loaded into memory into this data frame, DF. You can see that it has approximately 15,000 rows and 10 columns. Let's check the data type. So what type is of data frame? Yes, we see it's a data frame from Pandas code. Now to understand the data more, the first step we'll take is we'll explore the length and the breadth. We'll technically look what is the size of the data set. So Pandas provides a simple property called shape. Using the shape operator, we can actually check the dimension of the data frame. So as we know already, it has a dimension of 14999 and 10 columns. So what are the different columns in this? So we know there are 14999 rows, but we're probably interested in know what are the different columns present. If you just want to know what are the column names, we can just use the column property. df.columns gives us a list of actually all the columns in the data frame. Now, we understand that there is satisfaction level, last evaluation, number project. A lot of HR related attributes are listed over here. But then what values have actually been stored in these different columns? So to get a sneak peek of the entire data set, we can just look into the first 5 rows of the entire data frame. So if you are familiar with the Linux or Unix environment, you can just use a head command. So if I say df.head, and I pass in a number of, which will be the number of rows that we will return. So I'll say give the first 5 rows of the entire data set. So that is df.head of 5. So I can actually see 5 rows of each column in the data frame. So it tells me that, okay, the satisfaction level, I can see values like 0.38, 0.8, 0.11, and so on. I presume the values will be between the number 0 and 1. A similar story for last evaluation. Number of projects should ideally be distinct number of projects the employee has been associated during the stint with the company. Average monthly hours should be the number of hours he has clocked in for the company. Time spent with the company should be number of years. Work accident should definitely be a flag. Left should also be a flag to indicate whether he is still associated with the company, and so on. We see two categorical variables where we have sales, and the value sales, and probably a couple of more values. We don't know what are they yet. This should probably be an indicator of what department the employee is associated with right now. And then salary, indicating as low, medium, or probably even high. We'll explore this further, but then let's take a look at the bottom 5 rows. Probably it might give us a better perspective. So instead of df.head, I'll see df.tail and explore the last 5 rows. And we can see that, yeah, sales has the value support also. So this is most probably an indicator of which department the employee is associated with. And then similar values for which we have seen in the previous columns. To understand whether these columns have any other values like null values or missing values, let's use the command info. So info is a function provided for a data frame to see a high-level view of the entire data set. And here we go. We get information that the range index has 14999 entries and ranges from 0 to 14998. We can see that there are 10 columns and each of them have no null values. Just for example, 14999 non-null values. And this would be the data type for the respective column names. So we have float 64, N64, and then object. Object is basically a string object. And we can also see how much memory does this object use. But this gives us a very high level view about the object. But what if we want to know something about the entire data set in terms of summary statistics? There is another function called as describe, which actually gives us a high level sneak peek with additional details on all the numeric columns. So if we have a look over here, we can see for satisfaction level, which is one of the columns in the data frame, we have the count, the mean value, standard deviation, and the percentile distribution, which is min, 25, 50, and 70 percentile, and the maximum value, which is the 100 percentile. This gives us a better view of the entire data set. And as per as our previous understanding, we do understand that the values are between 0 and 1, and probably almost the same with last evaluation. Though we don't have 0, we do have a min close to it, and we don't see the values exceeding 1. Number of projects generally has a mean of 3.8 and has a maximum of 7. And with this same function, we can actually get a sneak peek into the other columns. What is missing over here is the categorical columns, or the columns which have a string value. That in this scenario would be sales and salary, right? We'll explore sales and salary, the categorical variables, in more detail later on. So let's look into a couple of data manipulation steps. So what are the different data manipulation activities that we would take on a data frame? Let's explore the data frame using the visual tool. So we have the variable explorer and we have a data frame over here. If you take the expanded view, we'll have a glimpse into the entire data frame. But this is actually a difficult thing when you have several other columns. When we have 10 columns, it's a relatively easy thing to use the visual tool. So what if we want to actually access a particular column? That's a satisfaction level. How do we do that? In Pandas, it provides an intuitive way to access each column. So let's say we have the data frame. We can access each column with square braces and the column name and codes. So we say satisfaction level. And if you press execute this command in the console, the entire column values are displayed in the console. Here we go. Now what if we want to slice out a couple of columns together and create a new data frame? We can do that saying, let's say we give a new name. We create a new data frame called df2. And let's say we plan to actually combine 2 different or 3 or 4 columns into a new data frame. So we have the existing data frame and we create a list of columns that you would like to actually create for the new data frame. Let's take the first one, satisfaction level. We can also have salary. We also have sales. So these are 3 different columns. Do we need to add any more? For now, let's park over here. If you execute this command, you can see that we have created a new data frame with 3 columns. That is the entire length, 14999 rows and 3 columns. And these are the 3 columns which we have selected. Let's look at the visual tool. And yes, there we are. We have the 3 columns which we have selected with the appropriate values. So what next? What if we wanted to access a couple of rows and a couple of specified columns? Pandas provides an intuitive way to actually go ahead and slice your data. So let's say we have the data frame df. There's a function called ilog. It stands for index location and it takes into account 2 arguments. First, the length of rows, and second, the length of columns. So let's say we would want the first 10 rows. So you would say 0 to 10. Now this will actually give us rows from 0 to 9 and 9 stands for the 10th row. The next parameter would be the columns. So let's say we need the first 4 columns. So we would have 0 to 4. Now in this way, we take a small portion from the existing data frame. We take the first 10 rows and we take the first 4 columns. If we execute this and we create a new column called as df copy. This is a new data frame which we created. You can see that the data frame has been sliced into df copy. And there we are. We have 10 rows, 0 to 9, and the first 4 columns. Let's say we want to access a couple of random columns. So if we take into account the same data frame, and let's say we were interested to create a data set with the first, the fourth, and the last column, and then the first 500 rows. How do we do that? Now, the row axis and the column axis are pretty mature. So by default, let's say, if you use defaults, so let's say we have colon, comma, colon. This means that it's actually taking into account the entire list of rows and the entire list of columns. We can actually say something like access from 5th row onwards till the end and from the first one till the 4th one. So it actually has a more advanced way of accessing your data frame. So this indicates everything from the 5th row onwards, and this indicates everything up to the fourth column. If you take into account and execute this command, you can see that yes, we have the first four columns, and then we have everything on the fifth column, fifth row. You can see a small reduction in the number of rows. Now, coming back to the original example, we were interested in extracting the first 500 rows and specific columns of interest, the first one, the fourth one, and the last one. So what do? We would say we need all rows up to the first 500 rows, right? So we start with the default and end with 500. Next, coming to columns, but since we need random columns, we can provide them as a list. So we need the first one, the fourth one, which is the third one in this scenario, and the last one, which should be the ninth one. If we execute this command, we have a new data frame with 3 columns. And these are the ones randomly selected based on our interest. The first one, the fourth one, and the last one. So this gives us an easy way to slice data. How do we create new data columns? How do we augment the existing columns? So let's say you want to actually create a new column. We could do that by providing a new column name. So we say column 1 for data frame is equal to 1. Now when we execute this command, Pandas looks into the data frame to find whether there's any column called as column 1. If it exists, it replaces the same column with a new value. If it doesn't, it creates a new column. So in this case, it will create a new column with the value 1. You can look into the same data frame and can see that there's a new column called column 1 created with the values 1 all over. So whenever you perform a column level operation, Pandas takes into account to replicate all of that across all rows. So you don't need to actually write a for loop and update this value across all rows like you would do it in a generic programming language. Pandas takes care of abstracting the entire scenario for you by just replicating the entire operation across rows. We could also create new columns using the existing columns. So let's look into the data frame once again. Taking an expanded view, let's think about a scenario where we want to create a new column which is a multiplication of number of projects and the satisfaction level, just to get a quantified impact of how much the satisfaction level of the employee impact the company. The more number of projects he's worked with, the higher impact. It may not make complete business sense, but the idea over here is just to showcase one additional data manipulation technique. So let's create a new column called as impact, which will be a multiplication of satisfaction level and number of project. So that could be done easily saying, we create a new column called df, give a name as impact, and we say df of satisfaction level multiplied by df of number project. There we go. If we execute this command, we can see that we've created a new column which is now created by augmenting 2 different columns. So impact is created by multiplying satisfaction level and number of projects. Now in some cases, you might actually want to delete a column. So in this scenario, you've already created a column which you don't really plan to use, and that's column 1. So how do we delete it? This is a simple command where we can say delete df and column name. So delete del, df, and the column of interest. So in this case, col 1. So when we execute this command, Python drops that column from the data frame. So we can see that column 1 doesn't exist in the data frame anymore. Also, there would be cases where we want to perform some sort of string operations on a column. So in this data frame, we have a scope to perform some string operations on the column salary and sales. Or in fact, we could actually augment or create a new column with a completely new business rule, which could be a string one. For simplicity, let's start with salary. Let's say we have all these values in lowercase. What if we wanted to cast them to an uppercase? Let's look into this. We could access the column and convert it to a string. So for example, we have df as a data frame. In data frame, we access a specific column of interest, and that in this case scenario would be salary. Now salary is actually an object. To invoke a string related function, we need to cast that into str, that is string. So the moment we say .str, we invoke the string related operations. And then we can call any string related function. So let's say we have plans to convert it to an uppercase. So if we just call the upper function, and if we execute this, we can see that all of them have been converted to uppercase. Similarly, the string library actually provides a rich collection of functions that could help us do any sort of string operation. So let's say something as common as string substrings, or searching a substring within the entire string, or concatenating two different strings, or converting to lowercase, or replacing a certain part of a string. All of these functions are easily available within the string library. I would recommend to all of you to explore what additional functions do we have in the string library for pandas. Before moving on, I would like to show you one more simple string manipulation. So let's say we want to create a new column called salary which is concatenating a new column. So we create df new salary is equal to salary. We convert it to an uppercase, and then we also concat that with new. This is just a demonstration to show how do we do string concatenation. This process might not make any business sense. Let's just have a look at how the outcome looks like. Now if you look at df, we can see that we have a new column called new salary, and that has the uppercase value for the salary concatenated with new. So how do we filter the data set? We've looked into basic data manipulation steps. Another data manipulation step would be to filter the data frame based on some condition. So let's say we have the data frame where we have several values for the column number of projects, right? Number of project. What if you have to filter values based on number of projects, and you want a data frame where we have values only more than 5? So from the description which we saw when we did a data describe, so if you remember, we did describe on this data set, and as an outcome of that, we are confident that we have around 7 as the maximum for number of projects. Over here, we can see that the number of projects has a maximum value of 7. So we want to filter the data frame. We can have only values more than 3. That is, we would like to have only values 4, 5, and 7 in the data frame. So what I can do is, we can create a new data frame, and we can say that we filter the data frame with the respective column. So inside this, we write a filter condition. We'll say df of number project greater than 4. You can actually write several conditions with a logical operation. So let's say you want to use and or operations. You can just use the round braces to actually separate the different conditions. So this is filtering the data frame just on one condition. And we can see that df new is a new data frame with 12 columns and 419 rows. Just to be double sure that the execution is actually correct, let's check what is the value that we have in the new column. That is number project. Let's take a max and a min. In fact, let's take a min first. So if you take a min and if you find values like 0, 1 or 2, that would be your surprise. And you can see that the minimum value is 5. So values 0, 1, 2, 3 and 4 have been eliminated. So the filter works successfully. You can in fact add several more conditions to the filter condition. So let's say you can have one more condition. You can just separate the same condition with round braces. And you can add an add condition or an or condition based on your requirement. Let's say we want number of projects greater than 4 and salary is low. So we say df salary is equal to low. These are two different conditions, and using an AND operator to separate them. You can see df new, we have around 2000 rows with 12 columns. On exploring the same, we can see that number of projects, and salary will have just the same value. Now, to ensure whether salary has just the value low, if in case if it has values like median, then our filter has not worked properly. So how do we do that? We want to ensure that the values in the column salary are just low. What we can do is, in this scenario, we have a function that returns the number of unique values in each of the columns. So for this specific column, let's extract the number of unique values present in them. So let's have df new. We choose the correct column. We have, let's say, salary. And we're looking at the number of this function unique provides us the number of unique values within that column. And we can see that it has just one value low. So the filter has worked properly. If we execute this command on the initial dataset, that is data frame, here we are supposed to get more than one value. And we can see that yes, we have values like low, medium, and high. Let's look at how can we sort the values. So if we look into the data frame, now since we are using the visual tool and since we have a relatively low number of columns, it's easy to handle data by looking into them. If you want to sort the entire data frame based on one specific column, let's say you want to specifically sort the data frame on impact, we can use the visual tool, but this won't be handy all the time. So how do we sort the data frame based on a couple of columns using the code? So we have pandas function which gives us df.sortValues. In this function, you first pass the list of columns that you need to sort on. So let's say we need to sort on first impact and then the number of projects, number project. Now, how do we sort it? Ascending or descending? We provide another variable parameter. We provide a list of values that acts as a switch for whether it should be ascending or descending. The first one, this is 0. The second one, also 0. Let's say we make it 1. It just reverses the process. And you can see that the values have now been sorted. Similarly, you can add more number of columns and more number of switches over here. The default would be ascending. So you can just ignore this and you can execute this command. And let's say we store it in a new column, new variable called df underscore new1 is equal to the sorted data frame. You can have the new values sorted and stored over here. So this covers a basic set of data manipulation and data exploration techniques. What have we learned so far? We have learned to load the data frame, looked into the length and breadth of the data frame, and understand basics about it using the describe and info function. We can then look into what columns we have, access each columns individually, create smaller data sets or smaller subsets with specific columns of interest and specific columns of specific rows of interest. We can also filter them based on a condition as per our requirement. We can augment existing columns into new values. We can perform substring operations on categorical columns. We can also transform or in fact perform mathematical operations on existing columns or create new columns using existing columns. That's a basic set of operations. Let's look at some advanced operations that we can actually perform on the data frame. Now, these advanced data operations could be something analogous to a SQL group by. That is, you're rolling up data. What if we want to find out the average satisfaction level for each group under salary? That is something which is analogous to a group by function in SQL. So how do we do that in Pandas? Let's take a look at it. Pandas comes with a group by function. So let's say we have a new column or a new variable called df grouped. We can create this variable column, we can create this new data frame with an aggregated version of the data frame at the salary level. So the quest is to find out the average satisfaction level for the different levels of salary. So we would first need to group it at the salary level. So we say df dot group by, and in the group by we provide the columns that we need to group it at. So in this scenario it's just one column, so we say salary. Now this creates a grouped data frame. We just provide one more switch. We'll say as index is equal to false, so that this column is not treated as an index, rather it would actually come as a column in the new data frame. Now once we group the data frame, we can actually summarize the data. So how do we summarize? We select the column of interest, and in this scenario we say satisfaction level, and we execute a summary operation. So let's say we take uh, just a random number, we take the sum of them, and we execute this command. We can see that the satisfaction level will be summed at this group. If we explore this variable, df group, we'll have three values: high, low, and median. And we'll see the respective sum of all the values under these three groups. Now, sum is not an appropriate one. We have to take mean. If we take mean, we can see the average values under each of these different groups. So we can see that the lowest number is for low and the highest number is for high, which makes sense. Normally, employees who are paid well are actually much satisfied than others. This could be taken to a further level if we want to actually group it at a multiple group level. So let's say if you want to execute the same exercise, but we want to group it along with salary also with sales. So for each department, we're trying to look into how does the satisfaction level look across different salary levels. It's the same thing, just with one extra level of grouping. And if you take into account, so we have for each value of salary, every department's satisfaction level. Now, since we have a lot of different values over here, it might be a little difficult to actually visualize and understand using this tool. The best way to consume this data is by plotting a graph. We'll get into data visualization in the next section. But then for now, we can understand that we can actually group at several levels. And in fact, we can also create additional new variables at a summary. Let's explore few additional data manipulation techniques. We've already explored group by, which is an equivalent of split group by. We have four more new functions to look at. That is merge, join, concat, and pivot. Now the names merge and join might seem counterintuitive, but then merge in pandas is equivalent to the same vanilla one which we have in SQL. So you have an inner join or you have an outer join. The difference between join in pandas is merge in pandas happens on a specified column and join in pandas happens only on the index. There's definitely a way to augment for that to be applied on a different column. Let's keep it simple. Concat is simple. We can horizontally concat two data frames or we can vertically concat two data frames. And pivot is the same one which you would have used already in Excel or R. Let's handle them one by one. The first one being merge. To explore merge, we need two tables or two data frames. One will be the left one and the other will be the right one. Left and the right data frames will be joined on a specified key. Now let's have df as the original table as the left table, which is right now having the shape of 12 columns. So let's keep the left table as df. Now this might not be necessary, but I'm just renaming the left table to df. So the left stands for the original data set. Now the right table will be the one which we create by aggregating something. Now from the same table, let's aggregate satisfaction level at the sales column. So we say df dot group by, and in group by we pass the column sales and we aggregate satisfaction level with the mean. Now one thing we need to add over here, like earlier, is as index is equal to false, because we need the sales as a column in the resultant data frame. If you execute this, we have the right table ready. We made a misspell. My apologies. Let's execute them once again. The right table is ready. Now, if we look at the right table, we have a table of 10 rows and 2 columns. Now the idea is to merge this table with the original table, that is the left table, on the column sales. Now this column, satisfaction level, let's rename this to something else. just for the sake of simplicity. So let's say right dot columns is equal to the original one remains sales, and the new one could be satisfaction index. Probably a fancy word, but that's fine. Now once this is done, I'll say tf merged is equal to pd dot merge. I'll provide the left table, which is left, the right table, which is named as right, and then the condition how. How in this scenario will be inner. The default one is inner. We can actually ignore this, but then let's keep it for simplicity. And then finally we'll say on is equal to the column on which we want the join to happen, and that would be sales. If you execute this command, you can see that tf merged over here is a data frame with 13 columns. The 13th column is actually the new column which we have added from the right one. Just explore it, take expanded view. We can see satisfaction index coming into the account for the new table, and this will be in sync with the sales value. So when the value of sales column is sales, you'll have an appropriate value for that satisfaction index. If you go down further and check for a different value of the sales column, you'll actually see the value of satisfaction index will be a different one. There seems to be some issue with the scroll. Now it's fine. Alright. You can see a different value of sales, that is HR, and you can see correspondingly a different value of satisfaction index. So the merge seems to happen alright. What next? You can play around with this merge function on left and right joins. It's exactly in sync with the SQL left and right join. If in case your exposure to SQL joins is limited, I would recommend you to have a simple walkthrough over the internet with a couple of SQL related articles or the join or the merge articles on Pandas. It will help you to understand the merging functionality in Pandas much better. Similar to the merge function, we have a join function. The join function in Pandas takes into account the index to join. So let's say we have a left table with 4 columns and 1500 rows, and a right table with around another 4 columns and 500 rows. Now both these left and right table, let's for simplicity assume that have different column names. So let's say a new left table, left one, is equal to df dot ilog, and we take into account the first 1500 rows and the first 4 columns. Similarly, we can create a right table, right one, is equal to df.ilog, and we can say we take into account the first 500 rows and probably the last 5-6 columns. So let's say we'll take everything 7 onwards. Now if you look into the shape of the left one and the right one, we know that we have approximately 1500 rows and 4 columns. Here we'll have approximately 500 rows and around 6 columns. Now if you do a join on these two data frames, they take into account the common functionality as the index. Let's say I would have a new data frame called join. Let's say the left one dot join the right one. Now the default is a left join, so I will say how is equal to inner. When I execute this statement, I'll actually get a joint data frame with around 500 rows and 9 columns. So the 9 columns are the first 4 from left one, the remaining 5 from the left, the first 4 from the left one, and the remaining 5 from the right one. If I exclude this, or in fact I make it left, I can see that I'll have 1500 rows over here. That's it. That's the difference between merge and join. Join practically takes into account the index of the data frame. On the same ground, let's explore concat. Concat is a functionality where you can horizontally or vertically concat 2 data frames. So as simple as it sounds, let's create 2 data frames which we can concat. Now we had previously created a group data frame. Let's create that again. So we'll say df grouped 1 is equal to df.group by. We'll group it at the level for the variable sales, and we'll take satisfaction level as a summarized variable. I'm using the name variable and the column interchangeably. My apologies. So I'll say satisfaction level, and we create a mean of that. Just to be on the safe side and make it simple, we create as index is equal to false so that we have a column name. So we have df grouped 1, which would be the sales and the satisfaction level. Similarly, we'll create another data frame, df grouped 2, where we'll have the same terminology, but instead of a mean, we'll take the sum. It will make no mathematical or no business sense, but just for demonstrating the functionality we have within pandas, I'm taking a sum functionality. Now the common thing between these two data frames is we have the same names for the columns. Now concatenation actually happens either vertically or horizontally. So vertically would mean that we have two data frames with 10 rows and 2 columns each. So the resultant data frame will have 20 rows and 2 columns. If it's a horizontal concatenation, it would mean that we have 10 rows and 4 columns. So pandas helps you provide the switch using the axis parameter. So we can use concated is equal to pd.concat, and we can provide a list of data frames. It could be one, it could be more than 2 also. So group 1 and df grouped 2. Now we provide the axis parameter. By default, it will take axis as 0. Let's have a look at axis is equal to 0. We can see that the concatenated data frame will have a new shape. Let's say concated dot shape. Here we go. So the data frame df grouped 1 and df grouped 2, both of them had 10 rows and 2 columns, and we are concatenating them on the axis. We have a resultant of 20 rows and 2 columns. Now if in case we provide the parameter axis is equal to 1, so now it will do a column level concatenation, which means that it's a horizontal concatenation. Now if we check the shape, it will be 10 rows and 4 columns. This is how we simply go ahead and append rows to a data frame, or we horizontally concatenate two different data frames. These functionalities of a data frame, we will be leveraging them very frequently in our data engineering activities during exploratory data analysis and modeling activities. The last one, which I would like to showcase just before wrapping up pandas, is the pivoting functionality. So pivot is something which you would already be familiar with if in case you have already explored Excel. So pivoting would be, let's say a scenario, we have two variables. We have probably explored this earlier, but then let's take into account once again. So we're creating a new variable, new data frame over here. Let's say data frame PVT. And we are grouping this on 2 dimensions, sales and salary. Now the resulting data frame over here, df.pvt, will have too many rows to actually go ahead and visualize. So if you remember, previously when we had such a lengthy data frame, I told you it's a difficult task going ahead and consuming this data frame. But this would have been easier if you have visualization in place. So if you go ahead and visualize this using a couple of the visualization techniques we have in Python, things would have been very simple. But alternatively, if you pivot this, things would have been very simple also. When I say pivoting, I mean if I enlist all the sales unique values vertically and all the unique salary values horizontally, and appropriately assign the satisfaction level as a matrix, it would be relatively easy for me to understand and consume the results. So once I have the aggregated results, what I would do is I can say I'll create a pivot. Now the pivot is created as df.pivot2 is equal to df underscore pvt dot pivot. We provide the index. Index is the vertical column, which will right now be sales. Now the horizontal value, that is the columns, will be in this scenario salary. And the values over here will be the satisfaction level. Now if we create a pivot, we can see that we have a data frame of index with the sales, the column names as the salary, and the corresponding satisfaction level for each of this. So how do you interpret this? When the sales category is management and the salary level is low, the corresponding satisfaction level is 0.611. This is a much intuitive way to actually go ahead and consume results, and it's called pivoting. You pivot across an index and you pivot across a dimension, which is columns over here. Before doing a pivot in pandas, it's important to aggregate the values, because if in case if it encounters duplicate values, it will throw an exception. So in a nutshell, we have covered a couple of basic data manipulation activities, and we've looked into also a couple of few advanced data manipulation activities. So merge, join, concat, pivot, and group by are a couple of advanced data manipulation steps that we have explored in pandas. Overall, we've spent quite some time in pandas exploring what are the possible ways of augmenting and transforming data into new forms. This entire exercise will come in handy in the next sections while we explore data. Now that we have explored pandas, it's time that we go ahead and explore data visualization. The next section, we'll take a shot at doing data visualization using the native libraries in Python. Before we start with data visualization, there's one small topic that I would like to address, and that will be useful going forward. Functions. I'm sure you've already heard about this, but let's take a minute to revise a few things. Function, in a nutshell, is a block of organized, reusable code that is used to perform a single related action. Now, the syntax of Python will be def define, the function name, the couple of parameters that we would require, the function suite, and finally return something if required. Now, I have showcased a simple example over here that is so something generic for most languages, but I would like to take it to a different level. Let's take a look at this existing example, and then we'll move ahead. What I'm doing over here is I'm creating a NumPy array of the size 5 rows and 3 columns. Now that NumPy array is transformed into a data frame which will have the same shape, 5 rows and 3 columns. And then I'm assigning the names to the columns as ABC. So list ABC will create a list of A, B, and C, 3 elements. That gets assigned over here. So the df data frame will have column names as A, B, and C. And I'm passing the first column, df of A, to the function which will actually add all the values in that column and return the value divided by 2. Now this is something very generic, but then let's look into a different example. So let's say we have a Python example. So we'll import pandas as pd, numpy as np. All right. I will create a simple numpy dataset np.array, and let's create a similar example. Let's say 1, 2, 3. Another dataset with 3, 4, 5. Another dataset with some random values like 4, 5, and 6. So this is 3 by 3 data frame. I would need to provide one more level of nesting, and there we go. We have the values ready over here. All right. So if we explore data, we have a 3 by 3 numpy array. I'm creating a data frame out of it. So let's say df is equal to pd.dataframe, and we pass the data into it. Now this creates a data frame. Now the problem is the data frame will have some random column names which will be index based. So if I just explore the values in df, I can see that the column names are 0, 1, 2. So I'll just give a fancy column name over here. Let's say df dot columns is equal to list of A, B, C. This is the same example which I had showcased in the previous example. Yes, it looks good now. So if in case you are intrigued by what happens over here, I'll just execute this statement separately. You can see that it actually creates a list of values A, B, and C. And this value gets assigned to DF columns. So now DF alone will have 3 columns A, B, and C. So it's simple. Now if I access DF A, I'll access the first column. There you go. You have 1, 3, and 4. Now let's write a function. The function will be to create a square root of the input value. Let's say define function foo. It takes in a parameter x, and then it returns x square. Probably something very layman, but the idea over here is to showcase how do we use this function in a pandas data frame. Now we just test whether this function works or not. Let's say if we do a foo of 4 and we expect the result 16. Okay, it's actually taking into account 4. My apologies. I just got confused with the... Yes. So in some languages, we use a caret symbol to symbolize the square root, square and square functionality. In Python, it is 2 consecutive occurrences of an asterisk. So foo is a function which returns the square of the input number. So we have passed 4 and we expect 16. And that's it. We have 16 over here. Now, what I would like to showcase is, in pandas, if you have created an external additional function, a custom function, and you are trying to apply that function to a specific pandas column, how do you do it? So generally, let's say you have df.shape, it will be actually 3 by 3. You have 3 rows and 3 columns. You can actually create a new column saying df of d. D is a new column. I can actually add a new value. And pandas internally takes care of assigning 1 to each row in that. That is, you don't need to actually go ahead. If you just explore df, 1 would have already been assigned to all rows. There we go. But what if you want to do something custom? You have to apply a square root or a square on each of the rows over here. Do you still need to go for a for loop? Not really required. That's when we have a df apply function. So what you do over here is, we'll say df of a new column, df of d, and we use the apply function. And in this function, we'll apply the foo function. So how this works, we are applying foo on the column d of df. So df doesn't have a column called d, so we go ahead and create a new column d. And in that new column, okay, my bad, we actually have to provide a column which is already existing. So we provide c. It will take into account the column c and will pass that column to the function foo, and this foo function returns a series where it has applied foo on each and every element of c. So if we just execute the statement, we can see that it has returned 9, 25, and 36, which is a very valid one. So the square of 3 is 9, the square of 5 is 25, and the square of 6 is 36. Now you can actually go ahead and apply this to the new column name. So you have df of t, and you have this function being applied to all the rows. So rather than writing a for loop, iterating and creating something different, you can use an apply function to apply a function across the rows for a specific pandas column. That's it. Short, sweet, and simple. Now let's get started with data visualization. Finally, let's explore data visualization. This is the last section in this module. And in this section, we learn to visualize data using Python's plotting library, Matplotlib. There are several plotting functions available within Matplotlib. Among the all, we would actually focus on 4 of them. We would explore scatter plots, bar charts, line charts, and histograms. Now this list is definitely not exhaustive, and there are several other important plots that need to be used in a normal data science exercise. A few important ones would be pie charts, area charts, violin plots, box plots, and probably a couple of others. In this section, we will restrict our focus on only these 4 and give you a strong foundation to explore the remaining on your own. I would highly recommend all of you to explore the remaining plotting functions that are available within Matplotlib. To get started, please start with scatterplot. We'll actually use a dummy dataset to get started with. So let's explore Spider. First, let's import the package. So we say import matplotlib.pyplot. There are two versions available. We have PyLab as well as PyPlot. I would highly recommend you to start with PyPlot. We import this package as an object called PLT, and now we also need NumPy. So we import NumPy as NP. NumPy will give us a lot of functions that will help us create random numbers. To create a dummy dataset, let's create two random x and y variables. So x and y variables, let's say we create a variable with random 50 numbers somewhere between 100 to 500. So we can leverage the NumPy's random library. So np x is equal to np dot random dot randint, and we will say a start point, let's say 100, an end point, let's say 500, and a number that we would need. So let's say we choose a sample of 50. Now this function generates random 50 integers from 100 to 500. Now we can do the same for y. Let's say y can actually have a larger range. Now from 100 to 1000, we generate any random 50 numbers. Let's execute them and see what kind of values we have in x and y. So in x, we have some values. I'm sure the length is definitely 50. In the same way, y also has some random values with a larger range. Now, since we have imported the pyplot object as PLT, we can use the PLT scatter function to build a scatter plot. So let's say PLT scatter, and we provide the x and y variables x and y. Now, if you plot this, we get a plot which is not so visually appealing. Yes, this is definitely random numbers. We have random x and random y. And as you can see, x is actually ranging from 100 to 500 and y is ranging from 100 to 1000. So what is missing in this scatter plot? On the cosmetic front, we have x-axis labels, y-axis labels, the chart title. These are the first things that will come to your mind. Let's use the internal functions to add these elements. So let's say we add a title. So plt.title, we add a normal chart title. This is a sample scatter plot. Alright, this looks good. And then we say plt.show because we have invoked several parameters. Let's execute this, and there we go. This looks good. We have a title now. What about the x-axis labels and the y-axis labels? Let's add them too. So plt.xLabels, there we have it. Let's put an x-axis label. Now this is definitely a random one, so we put any label over here. The same goes with y. We put a y-axis label, which would be a y label. Just to test the cosmetic elements, now we do the code and rerun it. So we have an x-axis label, we have a y-axis label, and we have a title. In some scenarios, we would want to change the color of these elements or the kind of style of markers. These elements can be tweaked within this scatter function. So let's say I add marker as a triangle. A triangle is represented as a caret in Python. So let's add the caret symbol over here and let us run it once again. Now we can expect the markers as triangles. What if we want to change the color? Let's add a color element too. So we say the color is inside the bracket, we add color as, let's say, red. And we can execute the code once again. There we go. We have the cosmetic elements updated. There are a couple of different scenarios. We'll actually have a combination of two different elements inside a scatter plot. How would that look like? So let's say we have a scatter plot of x and y has two elements. It could be boys and girls. And now we need the boys plotted as a triangle, girls plotted as probably it's a square. Let's try that. Let's try just a square as S and plot it out. Yes, that's successful. If we have two different elements, let's create an additional Y. Now since this is random, I'm sure we'll have a lot of variation over here. So we'll just execute the same code again. Now Y and Y1, both of them ideally would have different values. Now instead of writing the same code again, I'm just copying over here. I'm saying on the same x-axis a different Y, and I'm saying a marker as, let's say, squares, or let's say take triangles, and we take color as blue. On the same chart, let's have a scatter plot for boys and girls. This is just hypothetical data. Here we go. Using scatter plots, we actually try to understand the strength between two variables. So generally, let's say, had there been some relationship between the x-axis element and the y-axis element, we could have seen some sort of trend. That is, as in when x increases, y also increases. So a trend would have been like this: a positive increment trend, or a negative increment trend, which means that x and y are inversely proportional. Now, since this is random data, we don't see any patterns over here. But then this is just a demonstration to show how do we invoke the scatterplot function available within Matplotlib. Similarly, we can invoke a couple of other functions. Now that we have good amount of understanding of how to develop scatterplots, let's take a shot at bar plots. Now, bar plots are usually used to study the strength between similarly associated variables. So for example, let's say you are trying to understand the marks you have scored in different subjects. So on x-axis, you'll actually print the subjects, and on y-axis, you'll print the marks you've scored. And looking at the bar charts, you can actually understand which subject are you the strongest with, and which subject are you the weakest with. You try to understand the strength of these variables which are related to each other. Let's mimic the same using a random data set. Again, let's create a random x and a random y. Now in this scenario, since we have a bar chart, a sample size of 50 might not be ideal. Let's say around 10 different or 5 variables. So we create x as 5 variables. So we say np.arrange and we say 5. So this should create a list of 5 elements, an np array of 5 elements. Is that so? Yes, 0, 1, 2, 3, 4. These are 5 elements. And on the y-axis, let's create another random sample of 5 elements between the values 50 and 100. So I would say np.random int. I would give the starting point as 50, the ending point as 100, and my sample size is 5. And this will give me 5 random elements. Let's see the values once again. Yes, we have 5 random values corresponding to the 5 x-axis labels. Now to plot in Matplotlib, the x-axis labels first need to be indices. We can actually use the plt.bar function where we provide the x, the y, and then we can later on add the x-axis labels. First, let's just print a basic bar chart. So we have x ready, we have y ready, and we can do a simple plot show. How does it look like? Let's have a look. Here we go. So we have the x-axis labels as 0 to 4, y-axis between 0 to 100, and we have a random plot. Now these are actually, let's say this could be considered as subjects, and this is the marks scored in that particular subject. And we can say that confidently, subject 3 we have the highest marks, and subject 0 we have the lowest marks. Let's replace these values in the x-axis with some actual values. Let's say we would add x list as a list of 5 alphabets. So I would say A, B, C, D, E. Now this function, and I'm saying list of A, B, C, D, E, what actually happens over here is it creates a list of 5 elements from this string. I'll just execute this part, and you can see the terminal, it's created a list of 5 elements. And I'm passing this to xlist. So xlist is now holding a list of 5 character elements. Now to invoke the x-axis indices to reflect these list variables, we need to pass in these values to the appropriate parameters. Let's say we say plt.xlist, and we invoke the same indices to map to these list values. So the indices were actually x, and the corresponding values from them would be xlist. Now, if we run this, what would actually happen would be the x-axis indices are now mapped to the list variables, and we have the actual values over here. Now, instead of actually just alphabets, what if we actually create more meaningful names? Now, this could be something like, let's say, English. Second would be math. Third would be history. Fourth would be science. And fifth would be geography. Let's try this. Now we have new labels with more meaningful names. How does it look like? As we can see, the names are actually reflected to the x-axis indices. Now similar to the scatter plot, let's add a couple of more visual elements. Let's add the x-axis label, y-axis label, and the overall chart title. Those elements can be added over here. Let's say plt.title. Since these are dummy numbers, I'll say marks scored by John, a random name. We need the x-axis label, so we would say plt.x label, and that would be subjects, and the y-axis would be the marks scored. That would be marks obtained or scored. Now if we rerun this, there we go. We have a visually appealing chart where we have the x-axis labels, y-axis labels, and the overall title along with meaningful x-axis labels. Is there anything else we can do? Probably we can change the color. That element could be added over here. So we say color is equal to red, and there we go. We have an updated version of a bar chart. That looks neat. Now in some cases, there would be need to actually plot a stacked bar chart. Now for example, if you're continuing on the same scenario, assume that John scored marks in the first semester and the second semester, and we need to showcase the marks obtained by him in a single bar chart. We could actually showcase that in a stacked bar chart. So the first part of the bar chart will be the first semester marks, and the second part of the bar chart will actually be the second semester marks. So for that, let's create additional y variable, which will be the new marks for this new semester. So since these are random numbers, I'm creating just y1, which will have a new set of values generated compared to y. So if you compare y1 and y1 has 51, 96, 90, 92, and 86, and y would have comparatively different values. Now I can create additional code over here to actually reflect the stack bar chart. I would say instead of plotting xy, plot x and y1 with the color blue. Now just to indicate that this should be at the bottom, I'll say bottom is equal to y. So to understand is that the first semester marks will be at the bottom and the second semester marks will be at the top. Now if I run this again, I get a stacked bar chart. This has been fairly straightforward. We've actually learned how to use bar charts, stacked bar charts, and scatter plots. Let's look at a different type of a plot now. What about line charts? So line charts are one of the easiest charts to plot in Matplotlib. Now to have a line chart in place, let's again create a new dummy dataset. Over here, let's say we are trying to plot the percentage obtained by a student in 6 consecutive semesters. So over here, the x-axis will be the semesters. So let's say x is equal to np dot a range 1 to 7 separated by 1. So we'll have the values 1 to 6 coming up over here. Let's check it out. We execute x and we can see the value stored in x 1, 2, 3, 4, 5, 6. And this would represent 6 consecutive semesters. What about the y variables? Y would actually be over here the percentage obtained by him in 6 consecutive semesters. For simplicity, let's use the same function. We use the random int, and we have, let's say, the lower cutoff as 50, the upper cutoff as 100, and we need 6 different samples. So this would give us the percentage he has scored in his respective semesters. So 67, 87, 57, 92, 93, 91. Random, but then seems very genuine, isn't it? Now let's use the plot function. So PLT is the object, and we directly use the plot function and we pass x and y. Now if you look at this example, we have the line chart ready. So we can see that he scored really well in the second semester, then went down, and then took off again. Finally, in the sixth semester, he closed his college on a very good note. I mean, this is hypothetical and completely random, but I'm trying to carve out a story from the random data. Again, similar to the other charts, let's add cosmetic elements over here. An overall chart title, x-axis labels, y-axis labels, and then x-axis markers. So that would be almost a similar activity. Let's create the x-axis list. X-axis list would be a list of semester 1, semester 2, semester 3, semester 4, semester 5. Now this is not the most smartest way to actually create labels. There are faster ways, but I'm just a little lazy over here. Yes, so we have 6 labels for the x-axis elements. So we have semester 1 to semester 6. We already have the y-axis values. We need the y-axis axis titles. Let's create them. So we say first plt.xdix, and we map the list values of indices x to xlist. Similarly, we add an overall title. We would say overall college performance, and we add an appropriate y-axis label and x-axis label. That will be y label. Let's say percentage or GPA. Percentage would actually be better. And the x-axis label with semesters. Now the overall part looks good. Let's have it plotted. Looks better? Now in some cases, you would actually need markers. So rather than having a line chart, you would actually need a more visually appealing element. So what if we had markers over here? Now to add markers, all we need to do is we need to pass a third element to the plot function. So the plot function, which is right here, we add a third element. The third element over here, let's say, would be blue triangles. So we say blue and triangles, and then we plot the same function. Does it look better? Oh yes. But then probably we need a red line associated with this and the markers along with that. So let's do that. So instead of just having the markers, we'll say plot x and y with blue markers, and then we'll say just a red color or any color line. Does it look good? Kind of better. What if we wanted to change this color, the line color? Let's do that. So we add another element, red, to the second plot, and now we run it overall again. And there we go. We have blue markers in triangle. We have a red line chart. We have the x-axis label. We have the y-axis label. We just missed out one element over here, which is this x-axis list. and let's run it again. Now we have the semester values, and then we have the entire plot ready. So we're saying overall college performance for John throughout 6 semesters. This is how his performance seemed to be. In the first semester, he scored around 66. He shooted up in the second semester and then drastically fell down in the third semester. But then, after a lot of hard work, he picked up and he gracefully completed his college. That sounds like a fair amount of good story. Now, with this example, we've completed three important plots in using Matplotlib. We completed scatter plots where we study a relationship between two variables. It could be positively increasing, it could be negatively increasing. Second, we looked into bar charts. We looked into single bar charts and stack bar charts. And we tried to understand the strength of similarly associated variables. Third, we looked into the line charts with markers. This is where we understand the progress of an element through different states. So of an element over here would reflect marks, and through different states would reflect the different semesters during that course time. Last but not the least, we have one type of charting element left, and that would be histograms. Now, this list is definitely not exhaustive, but then let's look at one more example before we wind up this exercise. Histograms. Histograms are actually used to look into the observations frequency across different bins. So for example, let's say we have a class of 60 students, and these 60 students have scored a value of marks between 0 to 100 in a semester. Now we're trying to understand the decile distribution, that is how many students scored between 0 to 10, and how many students scored between 10 to 20, and so on. So a histogram gives us the frequency of observations in each of these bins. It helps us to understand how well the data is spread across the deciles. Let's take a random example again. Now instead of a random example, let's look into the previous example of satisfaction index which we had in the HR analytics dataset. So if you remember, while exploring pandas, we imported a dataset into DF, which was the HR analytics dataset. Now if you do a df.shape, let's look whether we have the same dataset in memory. Yes, we have approximately 15,000 rows, 10 columns, and one of those columns should be the satisfaction level. Do we have that? We do. So what we can do is we can actually, now since we know that satisfaction level is a score between 0 to 1, we can actually create 10 bins from 0 to 1. So these 10 bins will be a representative of 0 to 0.1, 0.1 to 0.2, and so on. The last one will be 0.9 to 1.0. And we can actually see where do we have a clutter, like majority of the employees fall into which bucket. Now this can be explored using a histogram. Now using a histogram is very simple. Now we have a plot function with histograms, plt.hist. Hist gives us a very simple way to plot a histogram. I'll just take a minute over here to walk you through the syntax. It will ask you for the x values, number of pins, and range. We can ignore most of them, and what we can do is we can just pass in the x values. X values over here would be df and satisfaction level. Now this would be a series of approximately 15,000 values, and we say bins is equal to 10. Let's try and execute this. Yes, we see 10 different bins, 0 to 0.1, 0.1 to 0.2, and so on till 1.2. These are 10 bars separated together. And if you look over here, we can see that maximum employees fall into this bucket, that is 0.7 to 0.8. There are a couple of employees who had almost zero satisfaction level. That numbers are pretty high, which means these are probably frustrated employees. And then relatively low number of employees between 0.2 to 0.4. And the numbers shoot up. Now this is how we study the overall distribution across different deciles using a simple bar chart, simple histogram. Now, like the earlier visual plots, we can also have cosmetic elements over here. And these would be as simple as the title, the x-axis label, the y-axis label. Let's say we have, my apologies, let's again copy them. and we can just tweak it over here. So let's say overall distribution of employee performance. On the Y label, we have frequency of, or in fact, you can just say number of employees. And in the Y x-axis, we can have satisfaction level. And now we can have the chart rendered once again. And we have a beautiful chart that helps us study the distribution of employee satisfaction across different levels. Intuitive, isn't it? So using simple plotting functions available in Matplotlib and with almost limited amount of reusable code, we have visualized a couple of different elements across random scenarios. We've leveraged line charts with markers, that is, and without markers. We've leveraged frequency charts, that is histograms. We've also looked into scatter plots, bar charts, and stacked bar charts. Now, this doesn't complete the entire story. There are several other plotting functions available under Matplotlib, and several of them are actually important. Few important can be easily called out as the pie charts, the area charts, and probably we might be using them sometime down the line. In the next module, where we will be exploring data, then we might actually come across a couple of different plots which we have not covered over here. But then these four charts or plotting functions will actually give you a strong foundation to explore the remaining in a very easy and intuitive way. I hope this module has been helpful. With this, we come towards the end of module 2. Let's take a minute to recap the entire content that we have covered in module 2. So we go back to the presentation and let's traverse back to the agenda and just let's do a check. Have we covered all the elements which we planned? We started with a quick recap. Right from module 1, we understood why is Python important and how did Python evolve into the data science fraternity. We took a quick recap to understand the evolution of Python in the data science fraternity. How did it start? From 2009 onwards, how did it progress? What packages propelled the use of Python in data science? Once we had a fair amount of background, we looked into the use cases where we need to use Python 2.7 or 3.5. After contemplating a fair amount of points, we understood that Python 2.7 is legacy and Python 3.x is the future. Given that our current exercise will not have any limitations due to the package support under 3.5, we plan to go ahead with Python 3.5. We waded through a couple of simple installation steps with Anaconda distribution for Python. We looked into simple steps how we can install Python Anaconda under Windows, Macintosh, or Linux. We also looked into the Spider IDE. Once we had Python set up on a system, we started learning Python with Python. We explored the different data types. We explored 4 basic data types and 4 advanced data types. The 4 basic ones being string, boolean, integer, and float. The 4 advanced ones being set, tuple, dictionary, and list. We had the basic data types and advanced data types explored. We also learned about 2 important Python packages, pandas and numpy. We looked into NumPy and understood how we can create 2-dimensional or 3-dimensional arrays, augment them, perform mathematical operations, trigonometric operations, and linear algebra operations. We also looked into pandas, and in fact we spent quite some time with pandas. In the entire course, we spent a significant amount of time for data manipulation and data engineering using pandas. We used different functions where you could go ahead, group by, merge, join, concat, pivot, and understand different data types. Slicing and dicing was extensively experimented in this module. Finally, we also looked into data visualization. We leveraged the Python's plotting library, Matplotlib. We used 4 different plotting functions to build a strong foundation in data visualization. We understood bar charts, scatter plots, histograms, and line charts. We also mentioned and detailed a couple of other important plotting functions, which I would strongly recommend the readers to explore on their own. We missed out on one important function, We discussed about functions, that how do we create custom function and how can we leverage these functions using the apply function on a pandas data frame. All in all, we looked into the length and breadth of Python. We explored the basic fundamental concepts that will help us to move forward. Now, with this fair amount of context in Python, I'm sure the next steps for you will be fairly straightforward. In the next module, we look forward to exploratory data analysis and statistics. I hope this module has been really helpful for you. Thank you so much for your time. Looking forward to see you in module 3.